All right, here we're working on a really tough integral and trying to approach it in some different ways. So we're going to look at this particular integral. We're looking at the integral of 1 over square root of 1 plus x squared dx. If you try regular substitution, it doesn't work out. If you try integration by parts, it doesn't work out. And if you try regular trig sub, it gets kind of challenging. And so one suggestion is to look at these things that are called hyperbolic trigonometric functions. In other words, they're kind of like sine and cosine, but they are a little bit different. And so we're going to look at a new function, sine h of x, which you can pronounce cinch, kind of like if you cinch up your pants. So e to the x minus e to the negative x over 2, and then another function, cosh, which is e to the x plus e to the negative x over 2. And the thing about these is you might be like, what the heck does that have to do with regular sine and cosine? The piece that they're related to is when you do derivatives, when you do the derivative of sine, you get cosine. When you do the derivative of cosine, you get negative sine, et cetera, et cetera. And so I just want to show you, if I take the derivative, e to the x stays the same. E to the negative x multiplies by negative 1 because of the chain rule. And if you multiply it by negative 1, that plus turns in, or that minus turns into a plus, and you can get cosh. And you can see the exact same thing actually if you do the derivative of cosh, then you get back sinh in the first place. So it's actually even nicer than when you did sines and cosines, because with sines and cosines, you took the derivatives, you have those pluses and minuses that pop up. When you do sinh and cosh, it just actually flips back and forth. There's no positive or negative thing going on. The other thing that's really nice about them and how they're similar to sine and cosine is with sine and cosine, if you do sine squared plus cosine squared, you get 1. If you do sinh squared and cosh squared, we got to do it in a special way, a specific order. I'm tripping over my words right now. If we do cosh squared minus sinh squared, we'll get a nice answer. So cosh squared means we're doing e to the x plus e to the negative x over 2 squared. Sinh squared is e to the x minus e to the negative x over 2 squared. So if I square it out, the first piece becomes e to the x squared, e to the 2x. Then I have 2 copies of e to the x times e to the negative x, and I have e to the negative x squared. And that's all divided by 2 squared. I'm going to subtract a very similar thing, e to the 2x, but now it's minus 2 e to the x, e to the negative x, and then plus e to the negative 2x over 4. And when we're looking at how these things work together, I can see that I've got a positive e to the 2x minus e to the 2x. I got a positive e to the negative 2x and a minus e to the negative 2x. Be very careful with this next part. I've got a minus and a negative. So minus negative makes it plus. So I actually have 4 e to the x, e to the negative x over 4. And that equals the number 1. You might wonder, okay, where'd the e to the x's go? 4 over 4 is 1. E to the x times e to the negative x. You add the exponents together, because they have the same base. You add the exponents together, you get e to the 0, and that's equal to 1. And so we have this really nice thing it's similar to cosine squared plus sine squared equals 1. It's just cosh squared minus sinh squared equals 1. Okay, we found the derivatives and talked about that. The next thing to talk about is an inverse function. Okay, so I'm going to create just a little bit more space. When we had an inverse function for sine, we just wrote arcsine. We didn't really even come up with any alternative expression. We just said the answer is arcsine. Here, we're going to have to work a little bit more at it because we don't really have a arccinch button on our calculator. Oops, I didn't mean to clear everything. Oh well. Okay, so let's look at sinh. So again, sinh of x is e to the x minus e to the negative x. I keep looking down because I always forget which one has the plus and which one has the minus. So what we're going to try to do is find the inverse function of this. So remember, the idea is that you've got y equals some function, and you want to switch which letter is the dependent variable and which letter is the independent variable, and then rearrange it. So I'm going to try to solve this for y. First thing I'm going to do is just get rid of my fraction by multiplying by 2. Next thing I'll do is multiply everything by e to the y. And the reason I would do that is because e to the negative y is another fraction. E to the negative y is really 1 over e to the y. So if I multiply by e to the y, I get e to the 2y plus 1 equals 2x e to the y. And this is actually a quadratic equation in terms of e to the y. E to the y is my variable. And I'm just noticing I made a mistake. I started with minus in the middle, and then I just wrote plus in the middle. So we're going to go through and switch that to a minus. I think we're going to be okay. Sorry, I just made a small mistake, but went and fixed it. All right, the next thing I'm going to do is I'm going to actually just use the quadratic formula, because this is a quadratic equation where it's e to the y squared, something times e to the y, and then a constant. So I can set up the quadratic formula, e to the y, and that's going to equal the opposite of b, positive 2x, plus or minus the square root of b squared, so negative 2x squared, minus 4 times a times c, which is negative 1 after I corrected my little mistake. And all that's divided by 2a. If I pull that up here for just a little more space, I have e to the y equals 2x plus or minus the square root of 4x squared plus 4, all divided by 2. And so I can simplify that down to e to the y equals x plus or minus the square root of x squared plus 1. You might be wondering where that last step came from. Well, the square root of 4 is 2, and both of the pieces on the inside of the square root had a 4. So I factored out the square root of 4 and then canceled it with the 2 on the bottom. So this implies that y is the natural log of x plus or minus the square root of x squared plus 1. You might notice I only wrote the plus. And the reason I only wrote the plus is because when you do the subtraction, you're going to get a negative value inside of the natural log, because the square root of x squared plus 1 is going to be bigger than x for most values of x. And so we just include the plus in order to get positive values. So all of this gives us the groundwork that we need to actually evaluate the nasty integral that we were asked about. We were asked about integrating 1 over square root of 1 plus x squared. What we can do is make a substitution. Let's make a substitution where we say x is sinh of u. So then I know that dx is the derivative of sinh, which is cosh of u du. The other thing I know is that if I do the square root of 1 plus sinh squared x, that I can rewrite that in terms of cosh x, because we had that nice little identity. I'll write it up here again. We said that cosh squared minus sinh squared, cosh squared of x minus sinh squared of x is 1. So let's substitute our dx, which is cosh u du. Let's recognize that if I add sinh x to both sides, sinh squared x, then cosh squared is 1 plus sinh squared. So my integral becomes the integral of 1 over square root cosh squared x, or cosh squared u, cosh squared u, times cosh u du. And that becomes, everything cancels out, and you get the integral of 1 du, which is just u plus some constant c. The last thing to do is figure out what the heck is u in terms of x. Well, if you notice, what is x even defined as? X is defined as the sinh of u. And that means u is the inverse sinh of x. And that was done right here. And we found the inverse sinh of x. So we end up with our final answer, natural log of x plus the square root of x squared plus 1 plus c. And the last thing I'll do in this video is just show you how, if you do take the derivative of this, always a good idea after you take an integral is to take the derivative, check your answer. If you take the derivative of it, you'll do 1 divided by the inside function, x plus square root of x squared plus 1, multiplied by the derivative of the inside function, which can just go on the top. 1 plus 1/2 times x squared plus 1 to the negative 1/2 times the derivative of the inside, which is 2x. Believe it or not, this actually simplifies down to the original integral. I guess I actually need to show that. That's not as obvious as I was kind of hoping it for. That's okay. Let's show that a little bit more. Let's show that in a little bit more detail. So I'll just erase some of this stuff down here on the bottom left, and hopefully this doesn't take too long. Sometimes I'm surprised by the little twists and turns. So, okay, we can rewrite our derivative like this. 1 plus x times x squared plus 1 to the negative half over x plus square root x squared plus 1. All right, I'm going to multiply top and bottom here by square root of x squared plus 1. Because that's going to get rid of some of the square roots there. So that gives me 1 times the square root of x squared plus 1 plus x, because the negative half power can cancel with the other one. And then on the bottom, I have x times square root of x squared plus 1 plus, if you multiply those two things together, you get x squared plus 1. Okay, so now what I need to do is somehow make that equal 1 over the square root of x squared plus 1. Oh, I see. Okay. Let's do this slightly differently. I'm not actually going to multiply out at the bottom. Oh, that's kind of cute how that works. I'm actually not going to multiply out the bottom, because if you look at the bottom of the fraction, it's x plus square root of x squared plus 1 times square root of x squared plus 1. In other words, it's something divided by itself with exactly what I wanted left over on the bottom. Okay, so that was a little harder to check than I first thought, but it still was good to go through the process of showing how such an unexpected integral can derive back to the original indefinite integral. Thanks for watching. Let me know what questions you have.